Okie dokie. So we're still working on the OV2640 stuff. Today I hope to start talking over it. Well, I hope to start talking to it over the I2C interface. Let's see if we can get the clock going. Well, no, hold on. We have the clock working, which is this, and we saw that there was an output, and I actually today I got the oscilloscope ready because I don't really trust all that much that logic analyzer that I have. So let's hook it up to something more decent, and let's compile this, load it into our board, and confirm we have the clock working. So we want to have it at least at 6 megahertz working, because that was according to the OV datasheet, which I should have somewhere here. OV2640 datasheet. No, which one was it? PDF. Yeah. But the thing was that the datasheet stated that it was minimum 6 megahertz, I think. So it can even go as far as this, depending on how many frames we want to squeeze out of it. And I guess we'll see. We'll see how fast we will be able to run this when we need to. But I think the minimum value that they specified was 6 megahertz for the driving clock, for the input clock that we provide from the microcontroller. What was this? Here. So that looks like the absolute minimum, with 50% duty cycle, typical minimum 45. Yeah, that's, we don't care about this for now. So, okay, the other thing is that I won't really be able to show you the oscilloscope output because it's the old, like a desk one. There's not going to be much that I can do here. So yeah, too bad, but I'm gonna try to describe the waveform as much as possible. Okie dokie. And of course, we have set our output timer to toggle the output pin that we hooked it up to our timer peripheral. So it's going to toggle over every overflow, and basically we specify to drive the clock at 6 megahertz. So that means that the effective frequency of our toggle is going to be 3 megahertz only. So if we want to obtain the 6 megahertz, we actually have to double the value in here. So maybe we can try a little bit faster. So can we do this at 20 megahertz, or are we going crazy in here? I think that should be doable. Let's hook our power and our programmer. Okay, so that's our output that we have in here. I just quickly going to try to recall what we've done the last time exactly. So this, the clock, the I2C, the timer. Okay, so let's just kill this. Let's flash this hello from init, and let's see what we are getting on the clock. We're gonna put it to measure, and we are getting more of a sinusoid, to be honest. So it's not really a square wave, and that's probably is because of the fact that we're connecting all of this on a shitty breadboard. The good thing is that our frequency is 9.99963 megahertz. So what we can try to do is to hook it up to some sort of like a transistor buffer. But the problem is that I don't think I will have such a fast transistor to drive it that fast. So essentially what will happen if the transistor is not fast enough, we will still going to end up with this little kind of sinusoid. But I did have somewhere a Schmidt trigger negator gate. So maybe this would so what I had was it's 7414, I think. Hex inverter with a Schmidt trigger, yeah. No. Yeah, so it's essentially something like that, but what matters here is this symbol. So basically that should take a weak distorted signal and square it as much as it can. Hold on, let me just find it quickly. Okay, so it's something like this. Just and let's see the pinout. This is exactly 74HC. HC datasheet. So it's this. And then we just push in the input from the clock. There, it's showing here. Okay, so we just pushed in the input. So basically, the pin that drives the or the timer pin, where the signal is coming out of the black pill. We hook it up to the pin 1, and on pin 2 we should have a more or less a square output. Is this visible here? Yeah. And it's not really all that much square. So we will try to lower this a little bit. Just a minimum 12 maybe. Pity I can't show this. Take a picture of it and maybe I'll paste it into the video later. Okay. So this is what we are having essentially. So let's hope that this will be enough. And then, so at least the frequency of it is 6.2. So then on the port pclk of the camera, we should see then some activity, because then that should start driving the data pins. So this is 7. Okay, so I don't see anything on the pclk pin, which is here. Am I showing this in the camera? So it's here. there doesn't seem to be anything, even though we do provide the clock, XCLK here. So this could be because we need to put some something onto the I2C. So we will try to get working this now. There. So we have the clock output, we're driving it at 6 MHz, so let's see if we can get the I2C talking to the camera. So this is the code that I've put in on the last stream, and we haven't really tested it. And just to clarify, the camera is using SCCB interface, which, as far as I understand, is I2C. It's just that it's, you know, OmniVision's license-free flavor of I2C. So hopefully it's going to be fully compatible with it. We don't need this and we don't need this. So hopefully it's going to be fully compatible with the I2C, but who knows? Those are just promises. So let's see if we can get this working. So this is the 400 kilohertz. As far as I remember, in the table in here, 400K should be supported. There was a timing diagram here somewhere. No, this is the P node. Clock frequency 400 kilohertz. So I think this is equivalent to the I2C fast mode. So we will see. So let's just camera RS, this. We need the lip and camera, so that the compiler starts picking it up, and we want some sort of driver for the I2C cam or the SCCB cam. So OV cam and it's probably gonna be generic over I2C. I2C, and we probably want some sort of internal address, which is going to be just U8, const SCCB address is, I think we have it here. So that's the register content. Cześć Dobuśki, co tam? Chodź Basku. Okidoki. So where were we? The slave address of the camera, which is this, and we want to shift this straight away for the I2C addressing. So we want some sort of way to construct this. So OVCam, I2C, right, it's generic over this. I2C. We're gonna put in the embedded hull traits in here in a second. So we want pub function new with our I2C instance, which will give us self, and we want some function init, which will do this, and we want a write, which self, and so when we are writing, we want to specify the register and the value. And that's going to be probably some sort of result that we want to return. Probably we're writing, so we don't care about this, and an error. And we want a read, option to read. So also this self and our register we would read from, and we want a result. Which will give us the register content and an error. Okay, so okay, so init nothing. So this create flash error. Yeah, we need so struct error. So that's actually going to be generic over E, because we want to preserve the I2C. So we want to preserve the error that comes directly from our interface. What other errors we want? Probably read write. We're okay. We're okay for the time being. That'll do. Yes. So here, that's going to be our error as well, like this. In a second, yes, that's going to be our error. So we need to pass in the error here as well. No, we will import the where is it? The embedded hull interface for that. Traits, I mean. No. API reference. I2C. yeah, it's in blocking I2C. Yeah, exactly. So this is what we want. So where I2C is read, that's from no. Embedded hull. I don't want it coming from the prelude. I just want it directly from embedded hull. What was it? I2 no blocking. I2C read, and we want write read. Like this. So we want to read. This and our write read. No. Oh, yes, exactly. No, just boom, like that. So let's implement our so self with our I2C and our address equal to SCCB address. Yep, okie dokie. Okay, so our reading and writing. So writing. So self dot is that it? Read temperature, read write. So this is for write. So just write address and bytes. Okay. So self address and bytes. So and this is going to be like that. And that gives us the result. So we will map error into our error I2C like this. Boom. Expected blah blah blah. And we want this and okay. Hold on. No, this requires the address, so that's wrong. So here we will have an address, and this is going to be register, and that's going to be our value, like that. And what's this? Expected weight found. Oh, do I have a mismatch? What do I have here? Imported. Oh, to 6. Expected. Oh, that's because it's self I2C. We're not using our I2C interface in the current scope. And if I perhaps you need to restrict the parameter. No method found. I'm not sure what's going on. Oh, because this is write and write read. Like this. Just got stuff mixed up. Okay, so that compiles and this. So maybe we can try to import this stuff here. Okay, and now let's do the read, which is the self.I2C dot write bytes to slave with address and then reasonable bytes to fill in the buffer. So we will prepare a little bit of buffer. We'll add the address, the bytes we wish to put in which is just going to be the register address, and our buffer, let mat buff r, and that's going to be our u8 1 buffer like this, and then we will map our error again, error I2C error, like that, and here we will result we will just return the single register. Yeah. So buffer like that. So expected result found this. Oh, yes. Okay, and this is expected value found built-in type. Oh, because we want to initialize it as this. This is okay. So maybe before we initialize this, there are two registers that allow us to verify the chip, if the I2C is even working correctly. Image mode, reset. This PID-H and PID-L, high and low, and their values should be this. So this is what they're showing in here. Okay, so that's probably depending on the chip. So it's either this or this. Okay. So const OV PID-H register is not value 0A 0x0A, and then our low is 0B, and OV2640 PID-H is, so high was 26 and 41, so it's 0x26 const, and the low one is 41. So that's going to be a quick and easy way to verify if we're talking to the pin or to the camera even. So pub function verify self, and that gives us a result as well. Result, and that gives us bool or error, like that. But okay, so that means here we will have a verify or unknown chip, like that. So here we will so let pt2 equals read OV2640. Yep, like that. That's going to be low. No, this is wrong. It's OVPAD. Yeah, maybe I should prepend it a little bit better. That those are registers. Okay. Like this. So this should be this, and then if pt2 equals OV26 and this equals to OV low, yep. So true, else error unknown chip. Okay, so once we have this, we can match. Cześć maluszku. Tak. Słyszałem. So match cam dot verify. So if it's okay. If it's okay, yeah, we can probably write this a little bit better. So actually we don't need to do this. I'm just gonna do this, so we're not being silly. And we know that in that case FMT, what was it? Print line, chip, verified, and error. Chip. Verification. Error. Like that. And we need to implement the DFMT. Implement VFMT for our error. And how does that look like? VFMT. We need format. Traits format. Okay, something like this. Boom. Use DFMT. It's in, yeah, directly in it. So format, formatter, and we need the right macro. Like this. So much. So I2C. The error itself won't have a formatter as far as I remember, because I don't think there's a STM32F4XX. I don't think the FMT is implemented for the errors in here. Optional true, so maybe there is a source. No. Source. It's not. Yeah. Oh, unless it's here after all. Well, we're still on hull 2. No. No, there isn't, so just gonna do it ourselves. And I2C bus error and unknown chip. Right, FMT. chip. What? Okay. Okay, never mind. There should have been this, like that. So there. Okay, verification I2C bus error. Verification error. So we'll need to have a look at why. So for that, let me just see if there's anything, if there's any activity on the pin when we're loading it. And I'm just going to use a oscilloscope for that. Okay, there isn't anything there. So let's try it on this, well, it's not slow, the standard mode, which is 100K, like this. Let's see if that does it. No, it does. Go back. It goes unknown chip. So it's actually reading in here. So let's see what it's actually reading. So DFMT print line. So pit high and no pit high and pit low. Pit high and pit low. Goes back 38 and 66. So what is it in hex? So 38 in hex is 26 and 66 in hex is 42. Oh really? So the datasheet lied after all. Okay, so this one was correct. Okay, so let's just adjust this. Like that. And we have chip verified and hello from it. Okay, so we're talking to it now. Okay, so how does our clock look like? So we don't have pclk. We have looks like we've lost everything. There's something wrong with my hold on. My probe got disconnected. There it is. So we have our input clock still fine, but we don't have our output clock. So presumably we need to start writing something into our init. And that's what I'm dreading, because those are some example initialization routines and there's a shitload of stuff to write in there. And to be honest, that looks way more than actual registers in the datasheet. So FF and 00, so that's the bank change register, which is this. So basically there are two banks in here, and one is responsible for like the DSP settings, and bank 1 is bank 0 for DSP settings, and bank 1 for sensor settings. So all of this applies to the sensor settings, and all of those table or registers apply to the DSP settings. So that's a lot to digest. So we probably need to agree on the format we wish to get the data out, and proceed towards this configuration set. So I don't have the pclk output, and I don't know, do we need to, enable it manually? To be honest, I would expect it appear straight away, and for the camera to start working, or to start spitting the images with the default settings. So I'm surprised that this is not happening. So for the very start, I think we could probably see if we can just do like a reset. So I would say that we can do a reset. Okay, so those are like separate kind of like modules within the camera, because each of those can be resetted separately. Okay. So let me just scan this quickly and see if there's something explicit that jumps out about the clock enable. So this probably is going to be of interest to us, this, because that's pretty straightforward format that we can work with as a, you know, to begin. So that will gives us the 1 byte of data. So that's the, I think, the luminance. So that's the grayscale of the picture, the Y, and then U and V are kind of like the, what's the word I'm looking for? Chrominance, I think. So that's, those two combined give the color to the picture. So we can just grab the byte that the camera spits out for each of the pixels, and then just work with this, and that should give us like right away a black and white picture that we can just spit it into our remote host, stick it into the BMP format or whatever for starters, just as a picture, and after that use for streaming, and then maybe this as well at some point, but I think probably we can go towards this. So UV enable and UV4 to 2 control 0. So maybe just let's make a note of that. So const OV2640, and that was C2 0xC2. So we will suffix those with reg. And this is going to be the val, like this. So const OV2640 CTRL0 YUV42, and that's the bit 4. So no, sorry, that's the bit 3. So 0x08, and that's going to be enable. That's the bit 2. So 4. Okay. Yeah. So val and reg. What happened here? What's going on? Ah, shit. Okay. Okie dokie. We don't need this, or like that. So init. So let's start actually writing stuff in here. So first of all, oh yeah, and the other thing we wanted is that reset, maybe to try it. So we want this. This is the something video module, DVP. Oh, that's also here, image mode. What was the DVP? I looked for it before as well. DVP. Digital video port. Has 10-bit digital video port. Okay. Okie dokie. So reset by default is this. Okay, not sure. Microcontroller reset. Oh yeah, and we have to remember about switching the this. So how do they initialize it? So they switch the bank to CFF. So they switch the bank, so it should be in bank 0 to CFF. Nope. To C. So why would they write into a reserved register? To E. Add VSH vsync pulse width. Line periods added to vsync with default vsync output width is 4 times t line. Each most significant bit count will add. Ah, Jesus, what does it mean? 2E. But how can they? Because this is for the bank change 1, and they haven't changed the bank, so that right shouldn't even matter. Only here they changed the bank. This is for JPEG init. This is for quarter VGA. They do the same here. Anybody knows what this magic means? Change 3C32. There isn't even such a register. Okay, seems to me that this is going to be a massive fail. 1100 0x11. Oh, don't tell me that I have to go through all of this errata as well. In table 13, change the description of a register bit clock to reserved. So this was made on some earlier version of this before it was fixed. Yeah, this is the beauty of going through the data sheets and stuff. Oh man. So hold on. Okay. No, we don't want quarter VGA because I'm not sure what that is exactly. So 2C. 2C. 0x2C. Nothing. 2E. Nothing. 3C. Nothing. 11. When used as a slave, register bits should be set to 1. When used in slave mode, COM7. Okay, so there is in fact 11 in bank 1. Clock rate control, internal frequency doublers on or off. Clock XV clock divided by decimal value within that register. So 11 is 0, so it's disabled. Because we have then, yeah, XV clock divided by 0 plus 1, okay. Then divided by 0 plus 1, which is divided by 1, okay. So it's off by default. So we don't need to change that though. At least we shouldn't have to. So 0, 9. standby mode. So normal mode is 0, output drive select. What does it mean, output drive? And they set it to 0, 2, which is 2 times capability. Okay, we can try that. Well, this is COM2. COM2, and this is 09. 09. So we want capability times 2x. So COM2 capability x2, and this has to be the 2. Oh, that's what it is. Yeah. Okay, so let's start writing those in that case. Jeez. Okay. So we need control register. Okay, so self dot write register, so OV so control register, and we need the OV this and control 0 and this. Like that, and we need self dot write dot OV no, that was COM, and we want this capability times 2, probably. And what are the banks? So this one is the bank 1. Self dot write, no, write. Oh, we don't have the bank register. Const OV bank select E8, and that was 0 FF, and the value, so const OV2640 bank, what was it, DSP, which was 0x01, and sensor, which was, no, the other way, I think. Come on. Zero is the DSP. Yeah, okay. So the control is the COM2 is in 1, which is sensor. The control is 0. Okay. So the control is 0. So OV bank select is OV2. Okay, I don't like this. This is going to be the bank 0, and this is going to be bank 1. So bank 0 and this is going to be bank 1. Yes. Okay. So clock input and nothing on output. Okay. So let's go through the rest of this stuff in that case. So 0, 4. The automatic exposure control register 0, 4. And what's the value here? 28. So 28. So one bit here and then horizontal mirror. Okay, don't care about this for now. 13. No 13. Ah, okay. Okay, that's getting silly. So 13, that's COM8. E5. So exposure control is auto. Auto manual control is auto. And bit 5, that's reserved banding filter. So COM8. Yeah, what was here about the which supports auto white balance and exposure and auto gain. Sometimes you might need to disable these auto functions to set manual control. And by default is C7. Okay, so we might want to enable this as C or E5 even. Okay. So E5, and that's in bank 1. So COM8, and it's the exposure control. So exposure and AGC control. Yeah. Exposure and AGC. So exposure, that was bit 0. X01. And C was bit 2, so 4. And that was COM8. Which is 13. Okay. Still no clock. Oh jeez, that's gonna take ages to go through all of this. Zero, 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 zero. Is there a register 00? There is. Yeah, we've just enabled AGC. Is there any like pointers here? 12 and 13. 12 and 13 provides a list and description of the device control registers. And 61 for read. There are two different sets of register banks. One register, yeah. And that's it. No initialization procedure or anything like that. Because right now I'm unsure, because on one hand, like, is it possible that we're not getting anything because simply the clock is bad? Or we're not getting any the pclk clock output because we need to somehow enable it with the through the SCCB. I don't know. Digital video port. Okay, so slave operation mode. The OV2640 can be programmed to operate blah. We use as a slave. Should be set to 1. And then the OV will use PW down and reset B pins as vertical and horizontal synchronization triggers supplied by master device. Okay, but like I'm going through some module that, for example, this pin is not exposed to me anyway. The PW down is power down, but it's for me to control the camera. So I'm just output formatter. This block controls all output and data formatting required. In general, timing generator controls the following. So supports frame exposure mode. Yeah, we don't care about this. Frame rate adjust, clock prescaler. By changing the system clock divide ratio and PLL, the frame rate and pixel rate will change altogether. Frame timing. The default frame timing is illustrated in figure 15 and figure 16. This block controls the interpolation of raw data to RGB and some image quality control. Edge enhancement, color space converter, denoise. Okay. Two methods are available to place into the power down mode: hardware power down, SCCB software power down. To initiate hardware power down, the internal circuit activity but does not halt the device clock. The current requirement drop to less than 1. So, is this the... Wait, keep on the risk? No. No, that's all of this is okay. Power down, input active high. So no. So COM10. Okay. Where was that control 10? Oh, sorry, yeah, it was COM10. So it's 0, 0, positive, positive, positive href. Data is updated at the falling edge of the pclk. Always output href. So we don't care about this at all. Common control. Okay, so let's try this image mode. I don't know why, it's just const image mode. That's DA. Okay, this is too long anyway. So OV image mode. So non-compressed output. So actually we don't need to change that either way. Because we want this anyway for starters. Like I feel that the default settings of this should be enough so that I just apply the clock and it starts spitting out. Okay, so no image mode. So okay, I think this is some sort of control byte as a like end of array specifier. JPEG init QVGA. So DA, that's what we just looked at, the image mode, yeah? They configure as 1, 0. So they enable JPEG output. D7. D7, reserved. So either this is based on some old before errata datasheet, or I have no idea why do they need this. DF, again reserved. What the fuck? DF 33. Reserved. Jesus. 3C. 0x 3C. Oh man. But they all have those. So that's bank 0, yeah. X2C and 0xff and RE and this is give. No fucking way. there's a pclk output. However, it is way slower, so let me just hook it up directly in here so that it's driven directly from the output pin. How do I disable the trigger? I think like that. Okay. There is some activity now on the vsync and the href pins, but the signal I see on the pclk is weird. But then I also see some activity on the data pin. Oh, hold on. Okay, PT, I can't show this. So that looks like a raw video signal actually. So this. Let me just move this. Okay, no. So those are no, those are proper pulses. Okay, so we're looking good. The problem is, so this is pin 1, 2, 3, 4, 5. Pin 5. What was it? Vsync. Okay, I'll just take a picture. So that's our vsync. So we have an output, or we managed to get an output. Oh, and also this is the pclk. So that's our master clock. Like that. And this is the pclk. Clock. Okay. So the worst part for me is that we managed to get it by entering a random values that I have no idea what they mean. Because they're the same in here and in here. They're not here. And I don't like to not know why something works. Okay, so So okay, for the time being, I say we are happy. So right now we need to work on those registers a little bit more. Get to a stage that we're actually getting something that we want, which is the YC. What's the word? The YUV format, the luminance chrominance stuff. And maybe we could also see if we are triggering those interrupts. So, for example, the vsync. So we need to enable it. Enable what's the crates docs. XTI. Come on, what was the XTI? Pin. What was it? From the implementation. XT pin. Yeah. Make interrupt source trigger on edge and enable interrupt. Interrupt, and we need not the dp.xt. Okay, so that triggers. If we can pass those pins in, we will be able to exactly tell which pins is being triggered when. So let's do that. So href enable interrupt and pt2 pclk as well, and then we need to pass those pins in. For the time being, we just stick it into local. So maybe for that it would be better to just struct XTI pins. Just thinking what's the best way to do this, but I think that will do for now. So href, which is the pin, and those are configured as that's useful. Into pull down input. Okay, so input push pull, pull down. Supplied generic argument. What did I use for those? PB5, PB8, and PB9. So PB5. So that was B and 5. Okay. And this, that was what, href and pclk. So href was 8. Oh no, sorry, vsync was 9, pclk was 5, href 8. Vsync. Vsync 9, href 8. XTI pins. Like that. Okay, it's getting crowded in here. X pins. CLK, href, and vsync. So we're getting the XTI pins. CTX local. We are triggering on falling. Actually, is that what we observed? Can't remember. What's the timing diagram set here? Yeah, negative edge, href. So href actually should be, so this should be on falling. Vsync is falling is fine. But the href, we are looking for the rising. So okay, let me just restart this because it looks like the rest analyzer stopped responding. And to be honest, after this I'm gonna have to run was a good progress though. We got this working. So now it's just a matter of figuring out the registers, what we want, and then start capturing the data out. And I'm gonna have to read a little bit about those registers because I don't like that I don't know what those registers really are. I'll go back here. Blah 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 blah. What's the API? Is high. Yeah, pin. So is high and is low. So pclk we want again. What was it? pclk we want is low. Well, it's just for now actually, just for the testing. Because once we implement it, we will trigger it, and we know that if it's raising, it's ready to read the data byte. But for now, it's fine. So actually, in here, in this case, if it's falling, yeah. So if it's low, pclk triggered, vsync and href, vsync href, and where was it? This was raising, so href that actually has to be is high. Struct EXTI declared as private. Okay, so it's happening. So it's happening, and we are being unnice because then we need to what was it? Clear interrupt, yeah. Clear interrupt pending bit. So XTI pins pclk dot clear interrupt pending bit. Vsync and href. Okay, so we are triggering stuff. We have the clock. We can talk to it over the SPI or the SCCB interface. Okay, so the next step is basically just be able to configure it exactly as we want it. So like I said, we want to capture the luminance just to get the black and white picture on the beginning to start with. And once we're capturing this correctly, yeah, once we capture this stuff correctly, we're gonna send it to remote host and start assembling it into pictures. And later on, we're gonna start to see if we can stream the actual video. Yeah, okay, so that's it for the time being, and talk to you later. Bye bye.